All right, welcome back to Essential Perturbation Theory and Asymptotic Analysis. Are there any questions before we get into method of steepest descent or back into method of steepest descent? Update on the homework. I'm still waiting for one or two homework submissions, and then I'll release the homework solutions, and then I'll give you your second homework assignment. So last time we were talking about the method of steepest descent. And remember, we did a few classes on contour integration and the theory behind that, trying to motivate, well, not motivating steepest descent, but just giving us the machinery, the equipment that we need to fully understand this method. Oh, and by the way, so I did just update these lecture slides, but I forgot to upload those to Canvas. But there are only some small changes, and I'll try to point out where I modified those. But I will be putting the modified, updated, corrected slides on Canvas shortly. So with this method of steepest descent, we're interested in approximating the value of an integral that looks like this as lambda is going to infinity. The structure of these integrals that we're looking at for the most part are usually the same. In this case, well, in all of the integrals that we've looked at so far have integrands which have some exponential component. The only difference now is that we're considering integrands that have the structure of some function, which is analytic h, times the exponential function e to the lambda. Lambda is our large parameter, times another analytic function rho. Remember, I said last time we were going to write rho as phi plus I psi z. So in other words, we're going to consider breaking rho into its real and imaginary parts. This contour that we're given here is something that is given, obviously, but the whole point of all of this is that we want to find a new contour which can express this integral, but in a way that's more amenable to the techniques that we've already invented or already introduced. The main idea is to, you can look at it this way: either you create a new contour or you deform this one, but not, and either way that you look at it, the integral is going to be exactly equal, but the new pieces of this integral that we're going to break this into are going to be amenable to study by Laplace's method, and using Watson's lemmas, we're going to be able to approximate these integrals for large lambdas. All right, so we said that we're going to construct a brand new contour called gamma, such that its first segment is going to be chi. And then we're going to have some subsequent segments that have the following property. Segments 1 and 3 are segments such that the imaginary part is constant on those segments. So these two segments are called constant psi contour segments for that reason, or at least I call them that. I don't know how universally that they're universally known as that, but that's what I'm going to call them. From there, we're going to have to introduce what's called a bridge contour. And the bridge contour is going to connect contours j equals 1 and j equals 3. We're not going to be able to say anything super nice about that contour, only that contour, or on that contour segment, the integrand is going to be, or the integral is going to be controllable. And the final point is that we want where gamma j equals 1 and 3, connect to the chi, the original contour, we want to have and of course we know that those are constant psi contours. We want to have the property that phi is a maximum at the point where gamma j connects to the original contour chi, right? So I'm going to review all this with a picture. But before I do that, the fact that we're creating this new contour structure, so our original contour was like this, that's chi, but we're creating new contour pieces, gamma 1, a little bridge contour, gamma 2, and then finally gamma 3 gets us back to chi. And we're going to traverse this thing or think about traversing it in the counterclockwise direction. That's the standard. Now, this contour, the new one that we've just created, lives inside of some bigger set D. And that on that set, our assumptions are that the integrand is analytic on that set. So remember here's our integrand actually here. It's comprised of this function hz, which is assumed to be analytic on that set, and e to the lambda rho z, and rho z is also assumed to become complex analytic on that set, meaning that it has one derivative and therefore via what we learned last time has an infinite number of derivatives on that set. So Cauchy's integral theorem tells us then that if we integrate over the closed contour gamma, which is all of this guy, I forgot to label this one here, this is gamma 3. So if we integrate over that closed contour gamma, we get 0. That means if we want to compare the original integral with what's left, we can write it like this. The original integral is the integral over the chi parameter, or the chi contour, but that can be written as because of this fact. And I also want to emphasize that whenever we have an expression like this, where we break this contour into other subcontours, then then we have a little result which says that this is equal to the integral of f of z dz on chi plus the integral over gamma 1 f of z. My brain only wants to write x's today. F of z dz plus ... Okay, so however many other contour segments you have. So what I mean by that is if we break gamma into the contours chi plus gamma 1 plus gamma 2 plus ... then that simply means that we can run the full contour by running first the contour over gamma, then the contour over gamma 1, or sorry, the contour over chi, then contour over gamma 1, the contour integral over gamma 2, and so on. All right. So basically what I'm saying is then this guy breaks up into a bunch of subintegrals, subcontour integrals, not over closed contours, of course. And then we can throw, because we have a 0 over here, we can throw those contours over to the other side. So that's why we get a minus sign here. So we find that this contour is equal to the contours run over gamma j, j equals 1 to 3, but with a minus sign now because we're throwing to the other side. And here's that bridge contour, which also gets a minus sign. So you can look at it as the contour integral over this contour chi is equal to this contour plus this one, this contour integral run the opposite direction, okay? So it's a way of doing what's called deforming a contour. So you can view it as running the contour either over chi or over this deformed contour. Either way, you're going to get exactly the same result. Now, one other thing I wanted to point out, if I run a contour in the reverse direction, that's just minus the gamma contour, then that's equal to the original contour with a minus sign. So that's why I've absorbed this minus, or how I've absorbed this minus sign on this contour definition here. And same with this. Here's the contour that I'm going to use for the problem that I'm about to introduce. So here's the original contour is chi here. And then I'm going to add these pieces. Gamma 1, gamma 2 is my bridge, and then gamma 3. And then we have to also keep in mind, what are the rules for these contours? Well, when I restrict psi to gamma 1, that's a constant called C1. And when I restrict psi to gamma 3, that's a constant that I'm going to call C3. I have no such controls over the bridge, but the bridge can become vanishingly small in this case, because we're going to send R, this sort of point of connection, off to infinity. And you can see, maybe you can see that as I do that, then these curves become closer and closer together until they merge at infinity. What are the other things that I need? Well, I said that phi has a maximum here along this contour. So phi and psi are both real numbers. When I evaluate them on these contours, or real valued functions, they're still real valued. What I want is phi to have its maximum along this contour at this point where it joins up with chi. That was one of my requirements. And same over here, where this contour gamma 3 meets the original contour chi, I want psi, or no, not psi, but phi, the real part of rho, to have a maximum point there, and then diminish away from that curve as I move in this direction. Again, these are things that I'm going to highlight with the example, so you don't have to memorize that or anything. All right, so here's the specific example that I want to do. I want to study the asymptotic expansion of this integral, 0 to 1, integrating the parameter s from s equals 0 to 1, e to the I lambda s squared. I want to study this as lambda gets large. So this is an integral that we might be able to apply. Maybe, let's see, this method of stationary phase might apply to this one. But we're going to try to get a full asymptotic. Remember, method of stationary phase only gives us one term of an approximation, whereas the method that we're developing now is going to give us a full asymptotic expansion. But in any case, this is the integral that we're interested in. And it turns out that this chi, so first, I'm getting ahead of myself. We want to transform this, or at least view this as a contour integral. How can we do this? Well, this is precisely the contour integral over a contour chi, where chi is just on the real line. And it runs from z equals the real value 0 to z equals real value 1. And then, of course, I think you can immediately see that these two are exactly the same. Okay, this integral over this real segment can be viewed as a contour integral, but we're still integrating over a real segment. All right, so now we have to understand everything we can about this function in the up here. So remember what our form was. This is lambda times rho z. So rho z should be for us I times z squared. So that's the function that we need to analyze and understand. All right, if I write z as x plus I y, which is the standard way we do this, then rho of z being I of z squared is just equal to minus 2xy plus I x squared minus y squared quantity. So to see that, it's not too hard, I think, but we can go through that. So if I have I squared z squared, that's of course just equal to, sorry, there's no I squared, there's just I. X plus, oh gosh, there we go. All right, and with the complex multiplication, you just do it as if everything was real in sight, and you just make the modification that I squared has to be minus 1. So I get I x squared plus 2xyi plus I squared y squared, which is just going to be I times x squared minus y squared, because this is a minus 1. Right? And then for the other part, we have what? I times 2xyi. And of course, that's an I squared there. So I just changed that to be minus 2xy. So that gives me my real part here, and the imaginary part is there. So that gives me these identifications. Phi is equal to minus 2xy, and psi is equal to x squared minus y squared. And I'm going to use the same abuse of notation that I talked about earlier. I'm oftentimes going to write this as phi of z and psi of z, even though they're really functions of two real variables. Okay, so that's the identification that I have to make. Now, in order to choose the contours that I want to deform chi into, or the contour segments, I need to pay attention to what these guys are. All right, so here are the contour segments that I'm going to pick, and then we're going to refer back to the diagram so that you can see that that's exactly what we're doing. All right, so remember, the contours gamma 1 and gamma 3 have to be constant psi contours. So they're actually not that hard to choose, because all I have to do is figure out what value of psi, what level curve do I have to choose. So if it's 1, then I'm just going to set these guys equal to 1 and then solve x for y, or solve y in terms of x. Okay, so here's my first contour that I'm going to construct. Gamma 1, that should connect point z equals 1 to the point z equals square root of r squared plus 1 plus I times r. So that's precisely this point here. And that's this contour that I'm going to construct. So how did I know what this point was? Well, that's because I know what the contour should be. The contour should just be y equals x squared minus 1. And the contour that I'm going to choose is, or where that came from, is just choosing my level curve to be psi equals 1. Now, why did I choose psi equals 1? Well, because at this point here, I have x equals 0, y equals 1. So I just have to find the connection that passes through that point. All right, so x equals 0, y equals 1. So that should just be, now why am I getting the wrong? No, sorry. X equals 1, y equals 0. Using the wrong Cartesian coordinate system. X equals 1, y equals 0. So this has to just be the contour psi equals 1. That's that branch right here. You might object and say, well, isn't there also a branch which goes down like that? And the answer is yes. But we're going to rule that one out because it's not going to satisfy our other requirements, namely that phi should have a maximum here when I go in this direction, when I go away from the curve chi. So if I choose it to be down this way, then actually you can show that phi is not a maximum, it's going to be a minimum at that point. All right, so that's the first contour. I choose it by setting psi equal to 1. That tells me what this curve should be. Well, it doesn't tell me exactly because I have to choose either an upper branch or a lower branch. And I'm telling you, you need to choose the upper branch. Solve for y in terms of x. That gives you that curve. And that also tells you where you're going to stop. So you can easily see that that's the point that you need to stop at. Now I'm going to parameterize this stopping by a parameter called r. And I'm going to make it arbitrary at the moment. So this point out here, right, the value of the imaginary point or the imaginary part is going to be r times I. R times I. And the value of x that gets me there, you can just solve for that value of x. Okay, so that's how I know to stop at this point specifically. That's my gamma 1. You start at z equals 1. You traverse a curve out to z equals square root of r squared plus 1 plus IR, where the curve is exactly equal to that. And another way of expressing that curve is to say that that's the curve where psi is equal to 1. Now, the bridge contour segment is going to be this little guy here. And that's just going to join this point and this point. This point we just named. This point is going to be along a line where x is equal to y. Okay, if I take where I'm viewing this as being equal to x and this being equal to y. It's just along this line where the slope is exactly equal to 1. So that bridge contour is going to connect z equals square root r squared plus 1 plus IR to this point, z equals r plus IR in a straight line segment. Straight line shot right there. Now, why am I doing this? What is a bridge contour doing? Well, remember that this is on this part of the curve, psi is equal to, now we know what that constant is. We know that constant is exactly equal to 1. Now on this part, on this contour, we're going to choose that to be gamma 3, such that psi on gamma 3 is equal to 0. So basically what we're doing is contour hopping. We're hopping from the contour where psi is equal to 1 over to the contour where psi is equal to 0. Okay, make sense? And the reason why we have to do that is because we have this second contour or this third contour which has the important requirements that we're looking for. So let's get to that. Gamma 3 connects z equals r plus IR to z equals 0 in a straight line shot. And that are on that contour, we know that psi is going to be equal to 0. How do we know that? Well, if we look at that point of the origin, that's at the point x equals 0, y equals 0. So that's going to be phi equals 0. There's a contour which connects phi equals 0 to this point, and all we have to do is figure out what that guy is. Okay, well, if we connect with phi, if we connect to that point phi equals 0, or sorry, psi equals 0, we have a bunch of choices because this guy's going to cross like this. Okay. So this is the one we want. We know that's going to be psi equals 0, but we also have a psi equals 0 contour going this way and that way as well. Meets at this this crossing point. Why do we want to go up in this direction? The reason why we want to go up in that direction is because we want to try to meet this curve or get as close to meeting this curve as possible. Okay, so that's why we choose to go up in this direction. Now we still have to check the other conditions, the other requirements that we had, namely that phi is decreasing along this curve as we move out. Now remember what we know about complex conjugates, or what do we call them? Conjugate. I forgot the term we used. In any case, if we take the real and imaginary parts, right, and we look at their level curves, then they cross orthogonally. Remember that? And the terminology is escaping me right now, but I'll probably think of it at some point. All right, so the curve that the piecewise smooth, simple, closed contour that we want is going to be this one, as we said. The integrand is analytic on any open set which contains that. No problem there. So all our theory is going through so far. This R is going to be arbitrary, but then eventually we're going to send this positive value of R off to infinity. And we'll see why we want to do that. We'll do that primarily for 2 or 3 reasons, but the main one is that this bridge integral across that part becomes vanishingly small as R gets larger and larger. Okay, so now we said that phi has to be decreasing along this contour as we move away from the original contour chi. So how do we know that that's happening? Well, I've drawn on here the level curves of phi. So these are level curves of phi, and level curves of psi meet these guys orthogonally. They cross orthogonally. So it just so happens that phi, as I go in this direction on these level curves, is a decreasing function. So I forget what the value of phi is here, but as we're going in this direction, we're going downward in phi. So as you move this way, it's downward. Okay, this is the downward direction. As we move out that way. That's why we've chosen this branch. If we look at this branch over here, then we're going to move upward. Okay, we move upward in phi. Here we're moving downward in phi. So that's going to guarantee for us that the other parameters that we asked for, namely that phi should be decreasing along this curve with its maximum here at chi. And same here. That's because these are the level curves of phi, and they're clearly going to be in the decreasing direction. This is called the method of steepest descents, or the method of steepest descent, singular, because we're going in the steepest descent direction with these contours. Well, that's not exactly true because this one's going in the steepest ascent direction, but you get the idea. Any questions about this setup so far?
Do we need phi decreasing so the integral, I guess gamma 2 doesn't blow up as we send, like start sending lambda to infinity or something like that?
Yeah, so the whole point is we want to get rid of the complex part, number one, and replace it with integrals that are only real and can be treated by our Laplace methods. And we know in those methods we had to have decreasing integrands or decreasing exponential powers in our integrands, right? So we need to convert this into something which is just decreasing and real valued. And this deformation of the contour is going to allow us to do that. At the same time, because this is decreasing, this is gonna become, because the integrand is going to be decreasing, this is going to become vanishingly small. Okay, other questions?
The condition you were looking for, was it ranking something condition for the optimal integration?
What did I can't, for some reason I'm blanking on it. Orthogonal conjugates. Orthogonal conjugates. I'm not sure why it took me so long to remember that, but that's, so the level curves of the real and imaginary parts are orthogonal to each other. Okay. And so we're using that, that fact here. All right, let's take care of the bridge contour integral first. By the way, the whole point of all of this is that somehow the deformation that we make changes this integral into something which is easier to deal with. And the easier here for us means we're going to change this into something which is amenable by Laplace's method and Watson's lemmas. Okay. But we do have to deal with that pesky bridge contour. And let's deal with that one first. All right, so we have to create a parameterization for the contour. Remember, that's how we compute contour integrals. We have to come up with a parameterization, and then we're going to use our transformation, which says that let's say we're working on, I guess it is gamma 2, some function fz, can be anything. And we're going to replace this once we have chosen a parameterization. T equals the starting point to the finish point, f of gamma 2t times gamma prime of t dt. So that's what we're going for. That is the, so we showed, well, actually, that's how we defined this integral in the first place. And that's what we're aiming for, a parameterization of gamma so that we can make this, this change of variables and actually do this contour integral. So the parameterization we're going to use is a very simple one. The real part, or sorry, the imaginary part stays the same. It's just equal to r, right? So the imaginary part up along this contour stays the same. It's just equal to capital R. The real part changes, right? Changes from whatever value we had here to this value. So I can simplify that or state that very simply as gamma 2 of t is equal to t plus IR, where t goes from square root r squared plus 1 to t equals r. Does it make sense? Square root of r squared plus 1 to t equals r. All right, so let's sub that in. So we need to know what is gamma 2 prime. That's just going to be equal to dt. Well, actually just 1 times dt. Okay, so that part there is just going to be dt. Right. Okay, so, and now we're integrating from t equals square root r squared plus 1 to t equals r. We're subbing in gamma 2 everywhere we saw z before. So z. And so this becomes t equals square root r squared plus 1 to t equals r, e to the minus 2 lambda t times r. So that's for the real part. And the imaginary part becomes e to the I lambda t squared minus r squared. T squared minus r squared. Okay. So now there's no free lunch here. We just have to deal with this integral. But the nice thing is, this looks complicated, but all we have to do is approximate it and show that it goes to 0. So how we do this is, let's take the modulus of that integral. That just gives me this. And let's move the modulus inside using that property that we learned, namely that if we move a modulus inside for a complex integral. We have this, right? The modulus moves inside, but the price we pay is we no longer have equality. We have a greater than or equal to. Okay, so that gets replaced there. But notice that this is just a unit modulus number. E to the I anything is a number of modulus 1 using what we know about complex analysis, or basically using Euler's formula. Modulus of this is 1, so that becomes 1, goes away. And this guy is already real and positive. So when we take the modulus of that, it's just itself. We can reverse the direction of these guys here. Let's see. Let's see. May have had to reverse this earlier because the way it's written, this might actually have a negative. I might have a little bit of a typo here. So whenever I reverse this to begin with, I think, or whenever I applied this modulus, I think I needed to reverse this guy. So I'll make that change. So basically, this is correct, but this part is not, I think. Right? Because if I integrate something positive, let's see, does this make sense? Well, let's see. Let's see. So this, once I make the replacement, is going to be a decreasing function, positive but decreasing. And R is certainly less than square root of R squared plus 1. I'm integrating a decreasing function. So I think to make this correct, I would have needed to have done this replacement earlier. Yeah, otherwise you get a negative sign, right? Okay, so I'll fix that up. No big deal. This is correct. Ultimately, it is less than this. And this can be integrated exactly. This is just an exponential. And it's actually a real exponential function. So you can just do the integral as usual. You get 1 over 2 lambda r e to the minus 2 lambda r squared minus e to the minus 2 lambda r times the square root of r squared plus 1. This guy, the difference here, we don't care what it goes to, but it's something which is decreasing as r goes to infinity. And this guy is the thing that we're most interested in. As r goes to positive infinity, this is going to 0. So this is showing that our bridge integral in modulus is going to 0 and not going to contribute to anything. All right. So that takes care of the bridge integral. It goes off to 0. And ultimately, it does that as long as we're sending r to infinity, which is what we're going to do. Let's take care of the integral over gamma 3 next. We're doing this kind of in a lopsided order, but that's okay. Remember, gamma 3 connects z equals r plus ir. It's running back in this direction, back to the origin. It connects r plus ir to z equals 0 in a straight line path. We know that psi is equal to 0 along gamma 3. We argued that. So we're going to consider the following parameterization of gamma 3. It's just equal to t plus I t, right? The real and imaginary parts are exactly equal to each other. And we run that from t equals r to t equals 0. That gets it done. So the integral becomes I3. Remember, I3 is going in this direction, so we need to pay attention to the sign here. The sign is important. All right, so this becomes the integral t equals r to t equals 0, e to the I lambda gamma 3 squared. So this is just putting in the definitions. Okay, and now we're going to break that into the real and imaginary parts. So you can see that when you do that, break it into its real and imaginary parts, the imaginary part we claimed is just going to be phi equals 0. And you can see that because you just get t squared minus t squared. So that guy is, in other words, 1. The real part is minus 2 lambda t squared. Well, we said, actually, if you want to go back to the definition, it was phi was equal to, what was it, minus 2xy. This is minus 2t squared because x and y are equal to each other along this line segment. So that's why we get minus 2 lambda t squared. Where does this guy come from? 1 plus I. Well, just take the time derivative of this. You get 1 plus I. Okay, so we have all the pieces. This, of course, is independent of t, so it can come out front. And now we're integrating t equals r to t equals 0 of e to the minus 2 lambda t squared. Now remember, we want to send to r to infinity. The reason why we start out without r going to infinity is because we want to use Cauchy's integral theorem, and that's for bounded domains. After a while, you get good at this, you just ignore that bridge integral to begin with, because it's probably going to be vanishingly small anyway. So we need to know how to deal with this guy as r goes to infinity. But I claim that this is just a standard integral that we can calculate, as I'll show in a moment. I do want to emphasize that that phi along gamma 3 has its maximum at t equals 0. That's because phi is just equal to minus 2t squared, right? So it's just, what does phi look like? If we plotted phi as a function of t, it's minus 2t squared, so it's looking like something like that, right? It's a downward parabola. Okay, so its maximum is at t0 where it connects to chi as required, check. All right, now we want to take r going to infinity, but I don't want to deal with the original integral that we have. I want to deal with minus, because that's going to flip 0 and r. So flip 0 and r, and of course, taking r to infinity, we get this integral. And this integral is a Gaussian type, and you can solve it. So if you forget how to do this, you can throw it into Mathematica, and Mathematica is happy to do this for you. You get minus I3. I3 is what I'm calling the contour integral where r is sent off to infinity. So rather than write lambda comma infinity, I'm just going to drop the r, or the infinity reference. So minus I3 lambda, that's the one we need, because again, the bridge contour goes to 0. So ultimately it's this guy that's going to be of interest to us. Minus I3 of lambda is this piece right here. All right, this part here, 1 plus I, is easy enough to find, right? So 1 plus I. This conversion is done so often, I thought I might show you why it's true, or how it's done. So 1 and I, right? So here's the point, 1 plus I. This can be written as square root of 2 times e to the I pi over 4. That's because this angle is pi over 4, and this length is the square root of 2. Right? So all I'm doing is writing this in the polar form. You guys remember polar form of complex numbers, right? Every point z can be written as r e to the I theta in a not necessarily unique way. you have to decide how you're going to choose theta. Well, in this case, theta is just equal to pi by 4, and r is square root 2. Okay, so that's why that guy transforms into this piece here. And I guess the half comes from doing this integral, and the integral is square root of pi over square root of pi over square root of lambda. So that takes care of our gamma 3 integral. Okay, and now we only have gamma 1 to take care of. Any questions before we move on to gamma 1? Okay, so for the integral over gamma 1, that's going to really finish up this problem. The whole point is we couldn't easily evaluate the asymptotic expansion for that integral when it was written as an integral over chi, but transforming it to these other contour segments is going to be easier for us. Wasn't clear how we would deal with that integral if we only had chi to work with. So this first integral is quite easy, right? It's just a Gaussian. There's no asymptotic expansion of that at all, other than to say, well, okay, it's kind of asymptotic to 1 over the square root of lambda. This one we hope to get a bit more out of. So what is the contour integral over gamma 1? So recall that gamma 1 connects the point z equals 1. So let me draw a picture again to remind us. So it's kind of going off in this direction like this. Here's our other contour, that's gamma 3, gamma 1. We have a bridge contour, but we don't really care about that because it's eventually going to go away. It's going to become vanishingly small. And the idea is we're going to take this value where they cross, or where we have that bridge, and just send r to infinity. So that means at the end of the day, we're going to be integrating all the way out to infinity along this contour. Well, we need to come up with a parameterization of that contour. That's how you do complex contour integrations. You have to come up with a parameterization for that curve. So the curve is this guy, y equals square root x squared minus 1 if we want to write it as a function of x. And as we said before, psi is equal to 1 along that contour. So we need to connect the point z equals 1 to this point out here, whatever the heck that is. And I guess it's square root r squared plus 1 plus I times r. So here's the parameterization that I'm going to propose. I'm going to, for various reasons, it turns out it's easier to put the t over here with y than it is to do it with x. You can do it either way. I could have written a parameterization like this. I could have done t plus, and then what would this guy have been? This guy would have been t squared minus 1 times I. All right. So what I did was I decided to do it differently, right? So this actually, I guess this one would have been, let's see. Yeah, this one would have been going from t equals 1, right? Because I'd have to start at t equals 1 down here, and then end up at t equals something or else. So what I did was I kind of viewed, I rewrote it so that starting at t equals 0, I'm here. Okay, so I just shifted my perspective. And I kind of thought about this curve as x as a function of y. And it becomes, for various reasons that are hard to explain unless you go down the dark path of trying it the other way, it's much easier to do it this way. All right, so I guess maybe you could just take my word for it that that works. So starting at t equals 0, I'm here, and t equals r, I'm here. Let's at least check that they make sense. So when I put in t equals 0, I get x equals 1, and I get y equals 0. And when I put in t equals r, I get x equals r squared plus 1 square root, and t equals r gives me a y value of r. Okay, so it all works out. Now, we need the time derivative of our parameterization for gamma 1. So take the time derivative, and you get t over square root t squared plus 1 plus I. It looks kind of messy. Okay. But let's not worry about that yet. Let's put it in and see what happens. All right, so this one we really are running in that direction. So we're going to integrate from t equals 0 to t equals r. Put everywhere you see z, put in gamma 1. So remember, our integrand was e to the I lambda z squared. So this is going to be gamma 1 squared. And I need the time derivative. Well, it's not really the time derivative. It's a derivative with respect to the parameter, but we're going to think about it as time. Why not? The derivative with respect to time of gamma 1 dt. All right, so just putting everything in there, we get this. Now, remember that psi is equal to 1 on gamma 1. So when you do that computation up here, you're going to get inside here, you're going to get e to the I lambda over here, plus this bit, which is the real part. Well, the e to the I lambda comes out because it doesn't depend on t at all. All right, so as I said, in both of these cases, when we're dealing with gamma 1 and gamma 3, we're back to dealing with integrands or integrals, which are mostly real objects. Okay, exponentials. The integrands are exponentials with real exponents. Now, that's not exactly true because I do have this guy lingering around, but that's not difficult to deal with, turns out. In any case, the e to the I lambda comes out front, and that gives us a contribution which doesn't depend on t. All right, now let's take r to go off to infinity. Remember, we're integrating 0, t equals 0 up to t equals r. So if we send r to infinity, we're integrating on this infinite, semi-infinite domain 0 to infinity. Nothing else changes. The only thing that we want to keep in mind is, well, does this integral exist for every lambda? And the answer is yes, it's a finite number for every lambda, so we're okay. Now we want to use Laplace type methods to deal with this stuff here, to deal with this integrand. Keeping in mind that as lambda gets larger and larger, we should be able to obtain an asymptotic expansion. All right, now the integrand is appropriate for, is of an appropriate form for using Laplace's method to deal with that. Remember, it has to be lambda, e to the lambda, times something which is essentially a negative function. For the Laplaces or Laplace integrals of the first type that we dealt with, it was e to the minus lambda t, and the second type 2, it was e to the minus lambda t squared. Do you guys remember that? Our Watson's lemmas of the first and for the first and second kind. We could only deal with integrands which look like this or like that. So more or less, this guy is looking like the first one, I guess you could, well, let's see. No, like the second one, actually, because it's e to the minus 2t, and this is basically like a t. That's adding another factor of t, for t large, right? So I guess it's kind of looking like that, although it doesn't matter because you can always transform one into the other through a change of variables. Okay. So we want to use the Laplace's method or Watson's lemma, however you want to look at it, to solve this. And we keep in mind, again, everything fits the prescription that we wrote earlier. We need to have phi be a maximum at t equals 0. That's where things get connected, right? This is where this guy connects onto the curve chi. So along this direction, phi is decreasing. And again, this goes all the way back to the picture that we had. This is the steepest descent path for phi. In other words, this level curve for psi is the steepest descent path for phi. And phi is getting more and more, it's going downhill, going this way. It turns out more and more negative. Okay, and so let's deal with this. To deal with this integral, we're going to make a very sophisticated change of variables. So this one hit me out of left field when I first started looking at it and thinking about it, but it's not as difficult as it looks. The idea is this. This piece here, what is this? Well, this is just like I, rho of z, evaluated on gamma 1. Okay, so this part here is just I, rho z, but where we set z equal to gamma 1. That's where that comes from. Now, what do we know about that? Well, that's just equal to phi. And phi is real when we stick to gamma 1. How do we know that? Well, because gamma, let's see, that's not exactly right. No, it's not exactly right. Let me back up. So what do we know about this? We know that this has a constant psi part, right? Along gamma 1, psi is constant. What is its value? It's 1, right? What does it mean to have a constant psi part? It means that your function is equal to 1 times I on that part. And its real part is decreasing. Okay, so I'm going to introduce a new variable called s, which is decreasing along that interval. I could have made it minus s squared, actually. And that would have kept this as more like a Gaussian type of problem. I could have said, let's choose minus s squared. I decided to use minus s. It doesn't really matter. As long as the most important thing here is to pick the right sign here. So s has to be positive, or at least not negative. Okay, but we have a parameterization of this gamma 1. It was exactly equal to square root of t squared plus 1 plus I times t. And actually, it doesn't really matter what parameterization we use. It's because of this structure here, it's always going to come out to be nice when we do this substitution. That's because we have to get an imaginary part, which is just 1, and a real part, which is going to be decreasing as s increases. Okay, so when we do this expansion, we get I gamma 1 t squared. Okay, so if you just expand this part out, okay, just square it, then you get I minus 2t square root t squared plus 1. This is actually what we expected, because this is going to be the real part, or sorry, the imaginary part where psi is equal to 1, and this is just the real part of rho, and we know that that came out to be minus 2t square root t squared plus 1. That's just that. So really what we're saying is we're setting s to be equal to this. All right, but now we can take advantage of the fact that we know how to, so let's take the time derivative of this guy. Remember what we have to do whenever we do a transformation of variables. We have to be able to do a replacement of dt with something involving ds. And so the trick here actually makes this computation a lot easier because we just realized that this is, so really all you're doing here is you're taking the time derivative of rho gamma 1 t, and that we said was equal to I minus s. Or let's see, so if I do, yeah, that's all we're doing. All right, so, and then we're going to take the, so essentially you take the time derivative of both sides. I minus s. And then you do like you usually do, and you pretend like you can write a ds dt as a fraction and split the two pieces up. And so this is what you get when you pretend like you can split that up as a fraction. Okay, so this is 2i, because remember rho is just equal to, oh, I made a mistake here. This is not I times rho, that's just rho, right? Remember, rho was equal to I times z squared. So this is just rho. All right, so all I'm doing is taking the time derivative of rho, setting it equal to the time derivative of this guy, using the fact or using the assumption that I can, once I have ds dt, I can write that as a fraction, and I get this. That makes replacing gamma prime t dt a lot easier. We can simply replace this, every occurrence of this. Notice that that appeared here with all of this. Now let me show you how this works out. So the transformed integral becomes just equal to this. I1 of lambda is equal to 1/2 I e to the I lambda, 0 to infinity, because we took r to be, we took the limit as r goes to infinity, e to the minus lambda s over square root 1 plus is ds. That's what you get when you do that replacement, keeping in mind that gamma 1 is just equal to this. How did I get that? From here. You have to take the right sign of the square root, by the way. So when you take a square root, you have choices of either plus or minus the square root, and you have to choose wisely. Okay, how do you know how to choose? Well, I'm not going to go into that in depth here. That's for another time, perhaps. I choose the plus square root, and so this is the integral that I get. Basically, if you take the wrong sign, something interesting happens. We'll discuss that actually when we go through the saddle point method in a little bit. You get a clear misdirection wrong when you choose the wrong sign. Okay, so now we can solve this part here. Now we haven't made any approximations at all. We haven't applied Watson's lemma or anything like that. Now we're going to apply Watson's lemma to evaluate this guy. So you might say, well, Watson's lemma doesn't apply in this case. And the reason is because I still have a complex contribution here. But the nice thing is the complex is nicely separated from the real, as I'll show you. So I'm going to apply Watson's lemma as if I can without any trouble, and we'll see what we get. If I want to do that, then what I really need is an expansion for this guy as a power series. Now, remember, in Watson's lemma, I didn't need that power series to be convergent for all s. It's okay if it's only convergent for a small radius or small values of s. That's not a problem. we have a nice expansion for this. So for this, you need to know a little bit about complex power series, which we didn't cover. But the nice thing is, basically, that binomial expansion theorem that I told you about before for real only variables works in the complex case as well. And it has the same conditions for the radius of convergence. Namely, this can be expanded as this binomial series expansion. It doesn't matter that this is this complex number is in here. It gets treated all the same. And so I get this expansion here. Now, this nicely separates the real and imaginary parts from each other. That's because the imaginary parts are clearly going to be the ones where I have the I. Now, let's see. I've written this in such a way as I have. There's something badly wrong with this, right? What are the powers here? That should be like a square and a cubed and a fourth power. So I forgot to put the powers on there. I'll fix that up and put those corrections in there. So I don't know where those guys went, but in any case, there should have been powers there, right? Z to the 0 power, Z first power, second power, third, and so on. So I'm not sure actually that I should be in each one of those terms either. I think I had a double aneurysm there. So whenever you have terms like I squared, right? If I have I squared, then it should be a -1. So this is this is badly wrong, but somehow I recover it in the end. So this is right. This is right. This is wrong. So if you just ignore this, then we're okay. Do we all agree? We'll all ignore that then. So this holds true for any Z with modulus less than 1. So I can just put a real number in there, namely S, and it still holds true. No problem. Binomial expansion. Now, by Watson's lemma, it just says that you can insert that power series expansion here for this guy in replacement, and then integrate term by term. And if you do that, then you get an asymptotic series. That's basically Watson's lemma in a nutshell. So I'm gonna substitute in that power series expansion. Part of that power series expansion doesn't depend on S, right? Namely, all of this part doesn't depend on S. And then I'm only integrating SK against e to the minus lambda S. So just these integrals here. That's nice about having done all this theory a priori. We don't have to worry about doing it again. All this method of steepest descent does is turn a complex contour integral into something which is amenable by Watson's lemma, or in other words, Laplace, into something which you can use Laplace's method to solve. Okay, so these integrals are found in Mathematica. Okay, Mathematica knows what to do in this case. There's no reason why you should memorize these things, but they're all nice integrals, and they can be written in terms of gamma functions if you like, and there are other ways to write them as well. I think in this case we get gamma k plus 1, but gamma k plus 1 turns out to be just equal to what? K factorial. All right, so we're good there. Now, that gives us an asymptotic expansion for I1. So the original thing we wanted is the I integral, all that business there. And remember, we need to reverse the signs. We need to change this to minus I1 and minus I3. Minus I3 was just that single object. Did I get the sign on that guy right? I3, where are you, I3? Oh, yeah. So minus I3 is 1/2 e to the I pi over 4 square root pi over lambda. Okay. And so that's just that term. That's the I3 part. This guy has no negative sign, so we have to introduce one when we do that replacement. And so there's our answer. Now, do I do... No, I didn't simplify this, but these are just the binomial coefficients that you can compute. Even though they're half integer and negative binomial coefficients, they're still tabulated somewhere and they're computable. This, I believe, is just, correct me if I'm wrong, that's just going to be k factorial, as I said. And so I get a nice asymptotic expansion, and all the heavy lifting was done by this deformation of the contour and then using Watson's lemma. Okay, so I decided to ask Mathematica if it could do this same problem. And remember, Mathematica probably doesn't know how to do contour integration, or at least it could do contour integration if you told it what contour to use. But I didn't say anything about any kind of contours or anything like that. I just said, give me, for this integral, integrating from s equals 0 to s equals 1. So this is the original contour integral, which actually wasn't a contour integral at all. Give me the asymptotic expansion as lambda goes to infinity, and give me 3 terms. And it gives you something which appears to be basically correct. So I checked this against what I had here. Of course, I originally thought that I had the right power series expansion here, but that's clearly not true. This should be z squared, z cubed, z to 4th. In any case, I flubbed that up a little bit. But originally, I did the calculation and compared the terms, and they come out to be exactly the same. Okay, so even though Mathematica is not telling you what it's doing under the hood or how it's getting it, it's probably not doing it via contour integration method. It's remarkably getting 3 or maybe even 4 terms of this asymptotic expansion. This is a hellacious nightmare, and I couldn't figure out why it was doing this, but it actually works out to just be all that I think is just 1. Yeah, so it really is just this term right here. Or it's, well, suffice it to say that this term here works out to be that simple term that I had here, I think. Okay, so that's where I'm going to end today. Method of steepest ascent is in the bag. The basic idea is you have a complex contour integral over a contour that you really can't deal with, and you're going to deform that into another contour where you can take advantage of the methods that we developed in chapter 3, namely Laplace's method, and use Watson's lemma 1 or 2 to evaluate the asymptotic expansions for those integrals. So this integral in particular was one that we could have dealt with using our method of stationary phase, but the method of stationary phase only gives you 1 term in the approximation. Namely, if you do method of stationary phase, you get just this term. But if I do this deformation method using steepest descent sort of principles, I can get a full asymptotic series expansion to all orders. Okay? Next time, we're going to talk about the saddle point method, and the saddle point method is quite similar to that, but instead of the rules that that we had for this contour integration, this deformation, we're going to come up with some slightly different ones. And one of the contours is going to have to go through what's called a saddle point of the phi function. So here, we were just interested in along this curve, we had to have phi being a maximum at this point and decreasing away. And same here, phi is a maximum at this point and decreasing in that direction. We're going to have those 2 principles in the method of in the saddle point method, but we're also going to want to run one of these contours through what's called a saddle point. And that's why it's called the saddle point method. We'll talk about that next time. I hope you guys have a nice evening, and we'll see you next time.